Imagine standing on a cracked floodplain 70 million years ago. A massive shadow slides across the ground from an animal that shouldn't exist. Incredibly, this prehistoric predator stands just as tall as a modern giraffe, yet it leans forward on its knuckles to carry the 250-kilogram bulk of a grizzly bear. For decades, rumors circulated of wingspans stretching past 20 meters, but careful paleontology has pulled those numbers back to Earth. The true giants possessed a maximum verified wingspan of 10 to 11 meters. To see the scale of that wingspan, look at this standard basketball court. If you place a top-down outline of the creature at half-court, the wingtips would stretch out and nearly touch both sidelines. Combining the towering height of a giraffe, a massive torso, and the wingspan of a small fighter jet creates a biological paradox. Mathematically, the dimensions of the animal make flight appear impossible. The problem lies in modern flight mechanics. A pigeon or a hawk runs or leaps off its hind legs, building enough speed for its wings to catch the air and generate lift. But there is a strict biological ceiling to that strategy. As a flying animal gets bigger, its body weight climbs rapidly, meaning it needs significantly more runway and heavily muscled legs just to reach takeoff speed. This graph plots weight against required takeoff speed. As mass reaches 250 kilograms, the required speed rockets into a danger zone. To launch like a bird, it would need to sprint 40 miles per hour. No bipedal launcher could generate that speed. If the physics of modern birds are applied strictly, this massive predator is permanently grounded. Early scientists were forced to view them as nothing more than flightless curiosities roaming the ancient plains. Scientists eventually moved past the failure of the hind legs and began analyzing the biomechanics of the creature's arms. This is the humerus of a giant pterosaur. Its structural density is an anomaly, 3 times more resistant to failure than a bird's. Steady flight doesn't require this. This reinforcement suggests the arms were engineered to withstand a sudden, violent, explosive load. This is the quadrupedal vault. The animal stands folded on all fours, shifts weight backward, and uses colossal forelimbs to push off like a pole vaulter. In a single motion, the body leaps forward, clearing the ground instantly, wings snapping open at the apex. Vampire bats use this exact four-limbed catapult method today. They crouch and launch into flight using incredibly strong arms. The same trick, shrunk down. By abandoning bipedal mechanics, pterosaurs bypass the limits of birds, using overbuilt arms to instantly hurl hundreds of kilograms into the sky. Once the violent launch is over, the giant effortlessly reaches the upper atmosphere. They rode invisible rising thermals to cruise at high speeds without the need for constant, exhausting flapping. Staying aloft at this weight required internal structural support. Running through the wing membrane were thousands of microscopic stiffening fibers called actinofibrils. These acted like battens on a sail, preventing the wing from twisting in the wind. A unique skeletal feature called the pteroid sat along the leading edge of the wing. This bone swung forward to deploy a specialized flap, altering the airflow. In wind tunnel tests, this structural adaptation increased aerodynamic lift by nearly 45%. This ancient high-lift system prevented fatal stalls. These creatures mastered graceful aerodynamics millions of years before human engineers developed similar devices for heavy flight. Giant pterosaur fossils are frequently unearthed far inland, in environments that were once dry floodplains and riverbeds. Because they could vault from flat ground, these giants were not tethered to coastal cliffs or updrafts. This ability recontextualizes their entire ecological role. These were active terrestrial stalkers that strode across open plains on all fours, hunting on foot and plunging their massive beaks down to consume small dinosaurs and lizards. This remains a living debate in paleontology. Some experts still question the exact speed calculations and the stress forces involved in the vaulting model. However, the four-limbed explosive leap is currently the only biomechanical model that logically supports an inland apex predator that needed to constantly launch from flat ground to survive. This timeline shows the scale of their success. Pterosaurs ruled for 150 million years, far longer than the gap between humans and T-Rex. During this time, they diversified into over 100 distinct species, from filter feeders to shellfish crushers. Their biology was so alien that when the first fossils were described, early naturalists dismissed them as the product of a sick imagination rather than the ordinary forces of nature. The reality is a gigantic reptile instantly catapulting itself into the clouds from a dead stop, bypassing the mechanical constraints of bird flight. Pterosaurs utilized a specific biomechanical adaptation. Their powerful forelimbs allowed them to evolve into the largest flying animals in the history of the Earth.